Hello and welcome. In this video we will be deriving the solution for the vibration of a Plucked string, and then I will show its animation using MATLAB. I wanted to make this video because I came across this solution in the textbook of mechanical vibrations by Rao, and I found it very cool. So I hope this video is interesting for you and it serves you well. So firstly, let me show you one of the resulting animations. If you want to see the real vibration of a Plucked string, you can search this YouTube video by Dr. Dan Russell, since our solution will not contemplate damping. The problem statement is the following. Find the motion of a string fixed at both ends when an initial displacement W0 of x, that is equation 1, is applied. The string has both constant tension P and mass per unit length ρ. The figure shows a string being pulled up to a certain height h at a certain point A along the x-axis, starting from one end of the string. The string has a length L, and W0 of x is an initial displacement composed of two equations, one for x between 0 and A, and one for x between A and L. Keep in mind that A must be between 0 and L. It can be 0 or L. The way to solve this problem is by using the wave equation, and for this case is c squared times the second partial derivative of w with respect to x, and that equals the second partial derivative of w with respect to time. W is our wave function, and it will tell us the displacement of the string at any point. And if you're not familiar with this equation, you can look up its derivation. It's not that complicated, and it basically describes how waves propagate through a medium, which in our case is a string. The letter c is the wave propagation speed, and it is defined as the square root of p over rho. That is the square root of the string tension over the mass per unit length. Equation 2 can be solved by the method of separation of variables, in which we assume the solution is written as the product of two functions, one dependent on each of the variables, where w of x and t of t are in the form of a harmonic function, where we have the sum of a cosine and sine with different amplitudes and same frequency. The amplitudes are constants a, b, c, and d, and the frequency for w of x is omega x over c, and for t of t is omega t. Omega is the frequency of vibration, and the constants a, b, c, and d are determined from the initial and boundary conditions. Looking firstly at the initial conditions, we have w of x at time equals 0, and that is going to equal w0 of x, and that is our initial displacement, and it was given in the problem statement, so we don't have to worry about that. And then we have the derivative of w at time equals 0 with respect to time, and that is going to be equal to our initial velocity, which in this case equals 0. And for the boundary conditions, since the string is fixed at both ends, the displacement has to be 0 at those points at all times. At x equals 0 and at x equals L, w is going to be 0. Starting from the boundary conditions, at x equals 0, substituting it in capital W of x, since cos of 0 is 1 and sine of 0 is 0, we get that a equals 0. And then at x equals L, substituting it again in W of x, we get that b times sine of omega L over c equals 0. Now, Since b cannot be 0 because it will give a trivial solution, sine of omega L over c has to be 0. Equation 14 is called the frequency equation, and the values for omega that satisfy this equation are the natural frequencies. We know that the arguments of sine that give 0 are all multiples of pi. So when omega L over c equals n pi, where n is a natural number, and it goes from 1 up to infinity, it will give us the frequency. Solving for omega, we get that omega n equals nc pi over L. The subscript n in omega corresponds to the value of each n, and as you can see, we will have an infinite number of natural frequencies. The solution Wn of x and t, corresponding to a certain natural frequency, is obtained by substituting the natural frequency into our assumed solution, and we get equation 17. That is the sine of n pi x over L times Cn times cos of nc pi t over L plus dn times sine of nc pi t over L. Remember that a equals 0, and note that the constant b is not there in equation 17. Since it is a constant, we can group it with the other two constants, c and d. Now cn and dn, and everything will be fine. Now this w of n is only valid for one particular mode or harmonic. A mode of vibration, or a harmonic for this case, refers to a specific pattern of motion exhibited by the vibrating object or system, and it corresponds to a particular natural frequency. So, to obtain the general solution, we have to superpose them, that is, summing all of the harmonics up to infinity, and we will get w of x and t, and that is expressed in equation 18, which is the sum from n equals 1 up to infinity of all the w of n's. Now we have to find what the values of Cn and Dn are. To do this, we take a look back at the initial conditions at time equals 0. So we will get for the initial displacement the sum from 1 up to infinity of Cn times sine n pi x over L. And for our initial velocity, w of 0 of x dotted, we will get the sum from n equals 1 up to infinity of nc pi over L times dn times sine of n pi x over L. Very similar stuff. If you have taken a differential equations course or some upper level math classes, you can recognize the form of equation 20 and 22, since these are Fourier sine series expansions of the functions w0 of x and w0 of x dotted, going from the interval of x between 0 and L. Using the formula for the Fourier coefficients, and you can look it up, we will get the two integrals shown in equation 23 and 24. Since the initial velocity is equal to 0 for the present case, dn will be 0, and w of x and t is expressed as the sum from 1 to infinity of Cn times sine of n pi x over L times cos of nc pi t over L. The final step is to obtain the value of Cn, in which we substitute both of the equations for our initial displacement, taking into account the intervals is specified for each one of them. The first one goes from 0 to a, and the second one goes from a to L. If we separate them for convenience and then add them, we can see that in equation 29, everything cancels out except for a sine term. And that leaves us with Cn equal to 2hL squared over a times L minus a times pi squared times n squared. And all of that times the sine of n pi a over L. So now finally, the motion for the string can be expressed as the sum from 1 up to infinity of 2 times h times L squared over a times L minus a times pi squared times n squared. All of that times the sine of n pi a over L times sine of n pi x over L times cos of nc pi t over L. As you can see, the full motion of the string is the product of three trigonometric functions, one a constant, one a function of x, and one a function of t. This is not something you see every day, yet here it shows up naturally. Anyway, now for the animation, we will not be summing up to infinity. Instead, we will be summing up to a number of terms, n, capital N. The larger this capital N gets, the better this approximated solution gets. For this section, I'm presenting you a series of animations featuring different values for all the parameters. This will allow us to analyze the behavior of the string under varying conditions. For the first one, we have n equals 500, h equals 1, l equals 1, a equals 0.25, which is a fourth of l, c equals 1, and t2 is the final time of this simulation, and it's going to be 2 seconds. As we can see, the waves propagate in straight lines, and since this is the undamped case, the string mirrors along the x-axis and keeps on going in cycles. Here is the same animation, but with the first 5 modes or harmonics visible. The governing mode is the fundamental, that is the one that corresponds to the first natural frequency. In this third animation, I want to show the periodicity of the vibration. The parameters are the same, but now L is 3 meters and T2 is 6 seconds. In order to find the period, we have to divide 2 pi by the first natural frequency, since the fundamental is the governing one. Omega 1 is pi over 3 for this case, and we can get the result by substituting the parameters in the equation shown earlier, and that will leave us with a period of 6 seconds. That's why T2 is equal to 6 seconds. That means that the string will return to its initial condition after 6 seconds. Now for this fourth animation, we are taking a look at A equals 1/2 of L, that is 0.5 meters, and we can note two interesting things happening. The first one is that the waves are now parallel to the horizontal axis, and the second one is that the even harmonics, that is for any number n multiple of 2, have disappeared. And the behavior of the waves gets more parallel the closer we are to the center, and the closer we are to one of the edges, waves get more perpendicular to the x-axis. Now I want to show the influence of the number of terms included in the final summation. For the same parameters as before, with n equals 5, we can clearly see a curve that approximates the string, but it wiggles a lot more out of it. Now, if n equals 10, the approximated curve wiggles less, but the curve still doesn't touch the edges nicely. I found that the closer you are to the center, the less numbers of terms you need to make a good approximation. Now I want to show what happens if we increase the wave speed up to 2 meters per second. And as you can see, everything is the same, but it happens a lot faster, as expected. With this speed, the string completes 2 cycles in 2 seconds, since the period is now 1 second. Lastly, I want to show what happens when A approaches one of the edges. For this case, we have A equals 1/8 of L. Now this is for A equals 1/20th of L. And this is for A equals 1000 of L. We can't make A equal to 0 or L because some of the equations diverge, but we can make A very, very small, sort of like a limit. And as you can see, the wave is practically vertical, as I commented earlier. I hope you enjoyed it, and if you have any questions, suggestions, or if you want to know how I build the code with MATLAB, be sure to let me know.